Yeah. Okay, hello. Welcome back to strong field laser physics and attosecond physics. For the online viewers, unfortunately, today you can only see a recorded session, but we have a live audience, so it's almost as if you're also here live. Okay, so in the last 2 weeks, we went through the introduction into strong field laser physics, and we prepared that electron dynamics, the motion of electrons in the laser field, is very crucial to understanding the general effects in strong field laser physics. And today we will build a little model on this that is surprisingly capable given the simplicity that it has. Yeah? And this model also has the nice property that it can be extended. And the more it is extended, well, as long as it's reasonable, the better actually the model becomes and can capture quite a few effects involving strong field ionization and also high harmonic generation, and even double and multiple ionization. Okay. What we will be building upon is, in fact, the analysis of the motion of the free electron in the intense laser field, in the oscillating electric field. And we will begin with a little revision of this. Yes, so, oh yeah, and before we do that, we will actually take another look at the atomic units that we introduced. Yeah, so does either of you remember what the ansatz to derive the atomic unit system is? Yeah, what is the values that we normalize? It's not the speed of light. What's the third? So the mass of the electron is correct, h bar, and yes, the unit charge, exactly. And then as a fourth unit, we select 1 over 4 pi epsilon 0. Yeah, so these are these 4 quantities. And as a consequence, we no longer measure length in meters, but we have a different length unit. You know what is an atomic length unit? Yeah, does anyone remember this? Yes, please. Say again? Yeah, the Bohr radius. Wonderful. Yeah, so let me take a few quick notes on this. Yeah, so here, revision, atomic units, and then we will also look at the ponderomotive potentials. Yeah, so we set h bar equals electron mass equals charge equals 1, as well as 1 over 4 pi epsilon 0 equals 1. Yeah, and then we can actually build a table. Yeah, so we put in this table here the atomic unit. So for example, length. This one we introduced, and this is now a Bohr length. A Bohr length is actually, the common symbol is a naught. And then we have the SI unit value. So let's say this is symbol. And here. Oh, sorry, this is the here. Actually, this is rather the expression. Yeah. So this is the symbol of the unit, and then we have here an expression. Okay, and then the SI value. This would be 0.529 times 10 to the minus 10 meters. And we already introduced the charge. That's the elementary charge, where we have 1.602 times 10 to the minus 19 Coulomb. Does anyone remember the quantity or the value for the speed of light? Yeah, or for velocity? Yes, and in atomic units? Yeah. It's actually 1 over alpha, yes. So the speed of, so velocity, this would be alpha c, 1 over, then c has the value of, c has the value of 137, the reverse of alpha. Yeah, and then this would correspond to 2.188, times 10 to the 6 meters per second. And another important unit is the energy. Yeah, what is the atomic energy unit? And that's 2 Hartree, which is twice the ionization potential of the hydrogen atom. So 27.2 electron volts. Energy would be, well, Hartree, which is E squared A naught squared 4 pi epsilon 0. And you see here that, of course, E is 1, A naught is 1, 4 pi epsilon, 1 over 4 pi epsilon 0 is 1. Yeah, this is 27.2 electron volts. And then, let's do 2 more units, namely time. Yeah, who remembers time? Time is roughly 24 attoseconds, and this would be h bar over the Hartree energy. Yeah, this is 24.19 attoseconds, and the way I remember this is that 2 pi atomic units equals the Kepler period in the hydrogen atom, which is 150 attoseconds, approximately. Okay, and another unit that we will use a lot is the intensity, the light intensity. Yeah, and this is a bit hard to remember, I suppose. So the value would be epsilon 0 times the speed of light times the that's the atomic unit of the electric field strength divided by 2. This is the formula how you can calculate this. And the numeric value of one atomic intensity unit is 3.51 times 10 to the 16 watts per square centimeter. So this is a very intense field already. Yeah. Okay, and another thing that was very important so far is the ponderomotive potential or ponderomotive energy. Who remembers the definition? Yeah, it's the cycle averaged oscillation energy of the electron in the oscillating electric field. Yeah. Ponderomotive energy. So I'm not writing this out, but the formula is, of course, UP equals the average over an optical cycle. This is the velocity of the electron. And so any constant term would be eliminated here. Yeah. And then 1 over t, integral over 1 cycle, mass over 2, x dot squared. Yeah, the result in atomic units would be intensity divided by 4 omega squared. So a typical example value is for a titanium sapphire laser. Yeah, so titanium sapphire laser, wavelength of 800 nanometers, and intensity of 10 to the 14 watts per square centimeter. That results in what value for the ponderomotive potential? So this is almost exactly 6 electron volts. And then another example would be the Polaris laser that we have here at the Institute. The wavelength is similar at 1030 nanometers, but the intensity is 6 or 7 orders of magnitude higher. And then this results in a ponderomotive potential that actually exceeds the rest mass of the electron. Okay. That much for the revision. Now we will begin with our semi-classical, or for the beginning, a classical model of strong field ionization. Okay, so this is chapter 2. Classical model of strong field ionization. And we begin with the direct electrons. So this implies that there are also indirect electrons. These we will discuss later on. Oh. Okay. So our starting point will be equation 14 from the previous chapter, where we integrated the equation of motion. Yeah, so this would be revisit equation of motion. Yeah, so we have x dot equals sorry, not minus. Yeah, E over m times the electric field strength, and then we'll just assume that we have a cosine. That we have a cosine that describes here our field. And now we can directly integrate this, and this is what we did in 0.1412. X dot of t equals minus E over m omega from the integration. Then the cosine becomes a sine. And here we had here minus E because this is the charge. Because never mind. Yeah, so if we integrate the cosine, we get a sine without a minus. So the minus here was correct because the charge is negative of the electron. Okay. And then what we did previously was that we ignored V naught, yeah, because we said we were only interested in the oscillatory motion of the electron. Now we will go one step ahead and not set this value to 0, but we'll rather use an initial condition in order to find a value for this. Yeah, and well, the simplest initial condition that we could take is, so we use an initial condition for the velocity at say t naught. Yeah, and of course we just set it to 0. Yeah. Assume initial condition equals 0. Yeah, and then we find for V naught that it equals E over m omega times times E naught times sine omega t naught. Yeah, and now you see that this value here now actually depends on this initial time t naught. So the constant velocity offset here depends on the initial time that we choose. And we had, I think there was a plot in the previous lecture here that actually showed this. Yeah, so what you see here is the electric field, and then there are two trajectories plotted. Yeah, in both the position, that's this one, and this one, as well as the velocities. And you see that the shape of the trajectory depends on the initial time that is chosen here. Yes. So this one, this trajectory here is started at this point, whereas that trajectory is started here. Yes, it's started not at a 0 point, but at some other point, and then this electron actually drifts away from the initial position. So this means it actually gains some net energy. So the observation that we make is that if an electron is somehow placed in the laser field, then it can actually gain some energy from it. And this is different to the well-known theorem that a free electron cannot absorb any photon. And this theorem can actually be understood if you try to make a balance of the momentum and of the energy. Yeah? So you try to fulfill momentum conservation and energy conservation. Then you very easily see that a free electron cannot absorb a photon. Yes? And so let's take a quick note of this. Yes, so we know that a free electron cannot absorb a photon. However, see above, an electron can gain energy from an electromagnetic field if it is somehow born in the middle of the field.
Is it like the photons are scattering of electrons and giving them their energy?
That's actually an effect that can also occur. Yeah? So this is actually a case where by scattering, you know, you've all heard of Compton scattering. Yeah, that way actually an electron can gain energy from the field. But here, this is different. And why this is different, we will see in a few minutes. Yeah, I mean, this is, for now, this is a hypothetical scenario because electrons are usually not just born in the field. Yeah, though there may even be exceptions to that rule as well at extremely high intensity. Okay. So, however, an electron can gain energy. Can gain energy from an electromagnetic field if it is somehow born in the middle of the field. And this chapter serves, the purpose of this chapter is to build a model for strong field ionization out of this observation. Make a model from this observation. Okay. A core question is, how is that electron born? Yes? And what is the answer? Does anyone have an idea what the answer is? Yeah, so of course we actually have atoms in our laser focus rather than electrons. Yeah, and so the electron can tunnel from the atom. And how this happens, that will be the topic of the next chapter. So we will not worry about it for now, but we will keep this on our minds and then return to this question in the next chapter. Yeah. Tunneling. See next chapter. Or see chapter 3. Okay. Now we're actually talking about what is essentially the photoelectric effect, and the photoelectric effect was somehow the birth point of quantum physics. So is that a reasonable thing to develop a classical model now for, well, a variant of the photoelectric effect? So this is the next point here. Yeah, so that's the Y classical model. And one point is, so in the usual scenario of the photoelectric effect, there is actually there are relatively few photons compared to the number of atoms. Now we actually have a whole lot of photons. Yeah, so in other words, the pulse energy is much larger than the photon energy here. Yeah, so we have many photons. Pulse energy is much larger than the photon energy, and therefore this photon character, this may actually be of secondary importance here. And then second, we studied the ponderomotive energy. At least we took a look at it, and we found that the oscillation energy is actually significantly larger, or can even be much larger if you think of the infrared fields, can be much larger than the photon energy. And this oscillation is a classical oscillation. Yeah, this was a completely classical motion. Yeah, so this is a classical motion. And then finally, we also looked at the excursion length. Yeah, so the amplitude in space that the electron does during one cycle, and we found that that number. I shouldn't write A naught because that is already used. So let's call it alpha naught. That's charge times electric field strength divided by m omega squared. This is much larger than 1, yeah? So larger than the size of an atom. The size of an atom. Yeah? And so there's some justification that we can actually treat the electron as a classical particle. Pardon? Oh. Okay. Yeah, so the excursion amplitude is larger than the size of an atom. And finally, there's experimental evidence, yeah, even from the earliest ATI paper, yeah, so from the first paper that showed this, what they called free transition, in the ionization of xenon atoms, there is evidence that the photoelectron energy is not always discretized, but may actually exhibit a completely continuous distribution. Yeah? Specifically, the data that was presented there was somehow looked roughly like this. The excursion length, that's the amplitude of the motion of the electron during one laser cycle. Yeah? So we saw here, up here, this would be, yeah, you have this trajectory here, down here, this one. Yeah, this would be the excursion length. Yeah, so this here would be 2 alpha naught. Okay, so in the very first ATI paper, what they showed was the kinetic energy of photoelectrons emitted from xenon atoms in an intense laser pulse, and they did the measurement for 2 different wavelengths. The first was 500 nanometers, so you have a photon energy of roughly 2.4 eV, and what they saw was one peak at low energy and then one at slightly higher energy. This year, this was 2.4 eV, but then they also measured, they performed the same experiment with 1030 nanometer light, and what they observed there was looked approximately like this. Quite a broad and continuous distribution, and there was no discretization, even though one would actually expect more peaks. Yeah, and so experimental evidence is on our site. Evidence, energy, electron energy distribution may be continuous. Yeah, so in this electron spectrum, there isn't really any sign of quantum effects, yeah, such as the photon energy. Yeah, so here this is electron energy, and then this is the number, so counts, photoelectron counts. Okay. Yeah, so much for the introduction. Now let's approach the model in more detail. So we have here 2.2. Yeah, this subchapter is called tunneling, two-step model, and a strong field approximation, which I abbreviate here. Okay, so instead of thinking of this energy diagram as we did in the first lecture when we introduced multiphoton ionization, we will now use a completely classical picture of an atom. And of course, this classical picture is a Coulomb potential. Yeah? So think of a hydrogen atom that's just one proton and one electron, and the potential is a Coulomb potential in which the electron is bound. Yeah. Consider an H atom. So we have potential V atom equals minus 1 over 4 pi epsilon 0 times 1 over r. And in atomic units, this would be simply 1 over r. Yeah. And yeah, what does this potential look like? Something like this, right? That's a Coulomb potential. And of course here it goes towards 0. V, and this is the radial coordinate. And now we add to this the potential of the laser. And the potential of the laser is, so the wavelength of the light is of course much larger than the size of an atom, and therefore the field, the laser field does not change on the spatial scale of the atom. And therefore the laser potential is very simple. V laser equals E times R. Yeah, so if you differentiate this by R, dV over dr, this gives the electric field. Okay, I guess I should use a minus here, because it's minus dV over dr. And this laser field, then draw this up here, is simply this.
It's like a dipole. Or
Sorry, what's that?
the potential of the laser field. Why it's like that?
Okay, the definition of a potential is that you can write the electric field is minus dV over dr. And if you plug this in, this is what you get. Yeah. Of course, these are these are vectors, and this would actually be then a gradient. But we're in one dimension here, so I'll skip the vector. If you use circular polarization, then it's actually or elliptical polarization, then it's important to take the vector into account. Okay, and so the resulting potential. I think I'll draw it again. Resulting potential is then, of course, it's called this V effective equals V atom plus V laser. And this is in atomic units, simply 1 over R. Sorry, this is minus 1 over R, of course. Minus E times R. Yeah, this is the effective potential. And it looks like so for orientation, I draw the laser here again. The laser potential, and then the sum of the two looks like this. Okay, and somewhere say here we have our ground state, and then this energy here, this would be the binding energy of the electron. Yes, this would be EIP, and of course this state is still also exists here. And of course it's somewhat distorted because the potential, the effective potential, is distorted. But the deeper the state is, the less affected it is. Okay, and what we can learn from this plot is that at small radii, yes, so say in this range here, yeah, here the atomic potential dominates. And then at large, R, yeah, say out here, and then of course all the way to infinity, the laser potential dominates. Larger R, laser potential dominates. Yes, so we have the situation that when the electron is close to the core, the laser field is not so important. When the electron is far away from the core, the atomic potential or ionic potential after the electron is gone is not so important. Yeah. So this is actually our remark 2. And then here, what happens in between? Yeah, so in between here we have chaos. Yes. Here in this region here, I guess the green I should have drawn a bit smaller. Yes, I think I'll fix this. The green box here. Okay, now back to the question. What happens? Yeah, so in between, in this range here. chaos. So this is the difficult region, and the solution is the solution. Well, you could call it elegant. You could also call it lazy. The solution is the so-called strong field approximation. And the strong field approximation means that when the electron is close to the core, we neglect the laser. When it's far away, we neglect the atom. And that's, of course, a lazy solution. Therefore, I put this in, well, in quotation marks. And the in between, this hasn't actually, I haven't talked about the region in between yet. The in between, we just assume that the electron tunnels. Yeah, so we assume that the electron tunnels from here to there. So this is would be the tunnel entrance. This would be the tunnel exit. Let's call this, no, entrance is not a good not a good one, because this you might think that this is the exit. So Eingang, Ausgang. So it's let's call this x0, and this would be xt for tunnel exit. Okay. So solution is, yeah, so first neglect laser for, sorry, this should be green. So here for small r, and this would mean r is smaller than x0. I just write tunnel entrance. Entrance, neglect laser. For r larger than tunnel exit, neglect atom, and then in between we have tunneling. And once again, this gives strong motivation for the next chapter, in which we will look at tunneling in more detail. And but what we will do here is we will continue on our model. Okay, so let's make some tests. Yes, we will test now whether these assumptions are reasonable. Yes. So tests. First, let's assume we have an ionization potential of half an atomic unit. So this is a hydrogen atom, and we'll assume that we're close to the core. Say x equals 1. Yeah, so this would be the Bohr radius. Yeah, so this would be a reasonable distance of the electron for a hydrogen atom. And now we'll just plug this into our into the equation for the potential. Yeah, so once again, the potential is 1 over x, or 1 over r, minus 1 over x minus ex. And now we ask the question, how strong does the field have to be that these contributions are equally strong? So the value of the ground state here is half an atomic unit. Yeah, and then so we have 1 over 2. Actually minus 1 over 2, since this is the binding, the energy is negative. And this would be then 1 minus E times 1, and so the electric field would have to be half an atomic unit of field strength, and that's actually a very intense field already. Yeah, so if we compare this, the intensity is E naught squared, and if here E is is 1/2, the intensity would be a quarter, and a quarter, this would be roughly 10 to the 16 watts per square centimeter. Yeah, so this is a very intense field, and most experiments were significantly below this. Yeah, so this is very intense. Yeah, we rather work with, say, an electric field of, say, 0.1 atomic units or so. Let us work with, say, electric field equals 0.1 atomic units, and this would be an intensity value of 3 times 10 to the 14 watts per square centimeter. Okay, then this is the first test. Now the second test is what happens after tunneling, yeah, when the electron is here, and for this we need to calculate the position of the tunnel exit. Yeah, the tunnel exit is well, we can make a very simple approximation here. Let us just let us just neglect the field here. Sorry, the ionic field, the Coulomb potential, and then the potential of the laser, E times x, and we have the potential should again, yeah, the electron doesn't gain energy during tunneling, yeah, so this should again be 1/2 times tunnel exit, and so the tunnel exit then would be 1/2 over electric field, and this could be, yeah, so for example 5, in our example here, this would be 5 atomic units, and there, then we can plug the 5 in here, and what we actually find in this example is that the numbers are quite similar. I just noticed I picked other numbers than in the script. So in the script, yeah. So what did they choose here? Ah, no, sorry. The mistake that I made is we should calculate the force. Yes, we should calculate the force, and then it's actually not so bad. Okay, so the Coulomb force, yeah, the Coulomb force is of course 1/x squared. Yeah, since the potential is 1/x, the Coulomb force is 1/x squared, and then this is 1/25, whereas the force from the laser, of course, equals the electric field strength, and this is, we said we wanted to work with 0.1, so this is 1/10, and so this is at least larger than the Coulomb field. Yeah. So by tunneling through this difficult region here, and just assume that tunneling is instantaneous, we go from one situation where it's sort of justified to neglect the laser field to a situation where it's sort of justified to neglect the atomic field. And the advantage of this is that our whole calculations become much easier than before. So from this we obtain. Yes, please.
If the electron is present at these distances from the nucleus, then they should tunnel.
There's a certain probability for the electron to tunnel, yes? Yeah, so you remember from basic quantum mechanics, yeah, one often calculates the transmission of a barrier, and we will actually do this also in the next chapter. And there's a certain probability for the electron to tunnel, and this probability, or you could also say this rate, yeah, so how many electrons tunnel per unit time, this rate, of course, depends on the size of this barrier. Yeah, this means the length and also the height. And it depends exponentially on both these quantities, because the wave function decays exponentially in the tunnel. Okay, so, and this is now basically the conclusion for the first part of, no, not quite. Okay, so this leads us to our two-step model. Yeah, two-step model. Where yeah, step 0 would be the electron starts from the ground state. Ground state G. Then step 1. The electron tunnels through the laser suppressed barrier. Through barrier. And step 2 would be that the electron is accelerated in the laser field. And this is what we have already calculated in the previous chapter. Free electron in an oscillating thing, not electron, electric field. And this means we simply have to solve the equation of motion. Yeah, as we have done above in chapter 1.4. Yeah, and in order to do this, we need initial conditions. Yeah, and one initial condition I already introduced in the beginning of this of today's lecture, namely the one for the velocity, where we assume that the velocity at time 0. Let me add here one thing. So we tunnel through the barrier, and this tunneling occurs at time t0. Yeah, t0. This can occur at any point in time, but of course there's a certain probability, and the probability depends on the shape of the potential, and the shape of the potential, because the electric field is oscillating. Yeah, the electric field is not always like this. When the field strength is reduced, then it actually becomes shallower, and we return to the standard atom. So this depends on time. Okay. This is now the initial velocity of the electron equals 0. I use here similar to 0 because we can, well, there are extensions or assumptions that this value can be slightly different to 0. And how can we justify this? Well, if we're here at this point, then the energy of the particle is completely given by the potential. So there's no kinetic energy left. Yeah?
So T0 is after the tunneling?
T0 is the time of tunneling. Yeah? So for now we assume that tunneling is instantaneous. And this justifies that we can completely neglect this area. Yeah? Okay, the velocity can be written as 2 times square root energy minus potential, and this is of course 0 at tunnel exit. And then the other thing is that we assume that, well, now actually the position, so this would be the tunnel exit. Yeah, the position of the tunnel exit. This can be actually calculated, but in many cases we can actually set this to 0, especially if you think of the infrared of the example at long wavelengths at 3 microns or so. We had an excursion amplitude of 100 atomic units or something of this order, and then if we start at 5 atomic units or at 0, it doesn't really matter. So I just write here approximately 0 or x of t naught equals tunnel exit. For this we can actually give an approximate expression, namely EIP over E, which is the one that we used above. Okay. Now there's a few more remarks that I'd like to make. First one is these initial conditions. There's actually experimental ways to manipulate these initial conditions. For example, using attosecond pulses. Yeah, there's a very nice experiment known as attosecond streaking, and this allows one to manipulate this. Attosecond pulses allow manipulation of the initial conditions. Okay. Second remark is, this is something I spent some words on. Yeah. So the question is, under what conditions the electron is most likely to tunnel? And so this is of course when the field is maximal. Yeah, you can, if you think back of multiphoton ionization, there we said that for xenon atoms, for example, we have an ionization potential of 12 eV. A photon energy, the photon energy is, for example, 1.5 eV. So we need something like 8 photons to go through the barrier. So this is a highly nonlinear function, yeah, of the electric field strength. And another remark is that we do not actually, like, what is the purpose of this classical model? Yeah, so we could also, I mean, a more accurate approach or more rigorous approach would be to solve the time-dependent Schrödinger equation. Yeah, so we already solved the Schrödinger equation for the time-independent Schrödinger equation to find the ground state of the hydrogen atom and also the excited states. And now we could add a time-dependent electric field and then solve the time-dependent Schrödinger equation. And this can be done. Yeah, however, using such a classical model has some advantages. In particular, it allows sort of an intuitive insight that a solution to the time-dependent Schrödinger equation is not always capable of providing. And finally, the original formulation of the strong field approximation is in a quantum mechanical way. Yeah, there you use the atomic ground state as the starting point. And then as the final point, you use so-called Volkoff solutions, which are the solutions for an electron moving in plane waves in an electromagnetic field. Which plane wave means in the absence of a Coulomb potential. Yeah, because the Coulomb potential would introduce a certain curvature. Yeah, and these will be the if there's time towards the end of this semester, Professor Paulus wants to give a quick excursion into the quantum mechanical description of the strong field approximation. Okay, we will now do a 5-minute break and then return to the second part of this lecture. Yes, and in the break you can take a quick look. You can think about questions that you may have for the material so far today. Okay. So